Hello everyone, my name is Shengan from Hangzhou Firstack Technology Company. Now we are the biggest DDU manufacturer and designer in China. I am technical marketing of Firstack, and today I want to share with you a special topic about IGBT and the double post test of it. So there are totally six lessons, and I hope you will like this video series. And also, I hope this video series can help you in your future study and work. If you like our videos, please don't forget to subscribe us and follow us after watching.
First lesson, I want to introduce the basic principle, background, and knowledge of double post test. So in first chapter, we need to know firstly why we need a DPT, the double post test, why this test is important during our designer process. So here in this slide, there is a statistic about the converter failure analysis. So from this chart below, we can see that IGBT and the gate driver take up the biggest area of this chart. It is totally around 60%. So it is 39% plus 19%. Yeah. And also there is some other failure factors. For example, the cooling system 15%, capacitor 9%, bus bar 6%, and also other failure factors 12%. So as for example, a converter manufacturer, maybe you will ask, how can I decrease or prevent the failure from IGBT and the gate driver? So to answer this question, we need to know firstly which factor exactly causes the failure of IGBT and GDU, which means the gate driver unit. From the classification in this slide, I list three the most important failure from IGBT and the gate driver. They are electrical failure, thermal failure, and others. So in electrical failure, we can see there are voltage failure, overcurrent failure, and in thermal failure, we can see the junction temperature problem, ambient temperature, and the temperature change, which means the temperature change in a very short time dramatically. It's like a temperature shock you can imagine. And in other factors, there is some mechanical factors like vibration, humidity, and mechanical stress. So today we only focus on the first two aspects. We want to know how to prevent electrical failure and thermal failure. Actually, this question is also the purpose of double post test, which means that from the double post test, we want to know how can we prevent the electrical and thermal failure by the test, and how can we evaluate the rate of it. So for any IGBT, you can get such detailed data sheet with detailed electrical and thermal parameters about IGBT and the diodes in it, including static and dynamic parameters. But in the actual application, we can see that normally engineer want to use this recommended parameters in the datasheet directly. The reason is that because all parameters in this datasheet are measured under a certain test condition, and this test condition cannot reflect the real application environment. Therefore, we need to test our complete system under certain test conditions, under certain external environment. Because in the IGBT, many parameters will be influenced by external environment. This is also why we say IGBT is not an ideal switch device. I list some important parameters below, which will be influenced by external environment, and then they will influence the dynamic characteristic of IGBT. So the first one is the collector current IC and the collector emitter voltage VCE, the gate emitter voltage VGE, and L delta, which is stray inductance. So as we know, the module cannot be used alone. It must be connected to the external circuit like the capacitor, inductance, and you need to use cable to connect them. And then you, on this component, you will find parasitic inductance. And the next two factors are the on-off resistance, and the last one is junction temperature. So the change of these parameters by external environment will inevitably lead to the change of dynamic characteristics of IGBT. So we need to evaluate based on the actual situation, and this is also why we need a DPT test. In conclusion, by double pulse test, we can evaluate IGBT parameters under specific operating conditions, whether the dynamic electrical thermal parameters are reasonable, and whether it will exceed our SOA in the datasheet. The SOA is a safe operation area. So now we know why we need a DPT and why it is very important. And the next question is how it looks like. From this slide, there is a very simple typology of cable connection of DPT test. Officially, there is no definition about double pulse test, but based on our actual work and experiences, the double pulse test is a method to evaluate the dynamic, electrical, and thermal characteristics of IGBT and the diodes in it through its two-switching process of IGBT. In simple terms, in a simple word, it is to simulate whether the switching parameters of IGBT at a certain voltage and current are in a reasonable range. So here we take a two-level topology as an example. As I said, there is a voltage source, the string inductance, and the half bridge represent the module, and we have a load inductance here. So we will test the bottom IGBT. So which means the bottom IGBT is a DUT, D-U-T, the device under test. So the top IGBT is given a negative voltage and to keep it always be off. In double pulse test, by adjusting our DC voltage, load inductance, and also the time of on and off, we can adjust the corresponding current and voltage. Now we can adjust our test conditions. The typical DPT waveform is shown in the right picture, which includes two on-off processes. The green curve is VGE, the gate voltage, and the blue is VCE, the collector emitter voltage, and the black is the collect current. So now we know generally how the DPT tester can be built and how can we make the cable connection. The next question is why the waveform is produced like that, why it looks like in this way. Then we need to go next chapter, so I will explain the complete DPT test process, which means also the principle of double pulse test. Now we go to this slide. This is the first stage of DPT test. From T0 to T1, we turn on the bottom IGBT, and the top IGBT is, like I said, it will be always off. The total DC bus voltage applied to the load inductance. The current through inductance will rise linearly, flow through the bottom IGBT, and it will follow the below expression. The current is equal voltage times T1 divided L, which the I is the current through this red path, and the U is our DC voltage. The T1 is the time duration between T0 to T1, and L is our load inductance. So it's a very easy process. So we can go to next part, next slide, which we will go to the time duration between T1 to T2. In second stage, now from T1 to T2, the IGBT is turned off, and the load current, as we know, cannot change suddenly due to the appearance of the inductance. So the load current starts flowing from the inductance to the top diode. As we know, for each IGBT, we have a body diode, corresponding body diode in the module. And the inductor and the diode circuit has also a low impedance. Therefore, the current will drop slowly, but it won't drop very dramatically. And from the right picture, we can see the dropped current, which is shown as this dotted line. Normally, from the real waveform, we cannot see this current because our current probe is placed on the emitter of the bottom diode. If you want to see this current, you can move your current probe to the top emitter, and then you can see this current. Of course, you can also use two current probe to check them simultaneously. And the next stage is at the moment of T2. The IGBT is turned on again, and the situation now is more complex. There is two current flow paths. And the first one is through the load inductance, which is similar compared to the first on process like T0 to T1. And according to the diode properties, there is an extra reverse recovery current from diode to IGBT. This current is caused by the diode own characteristic. As we know, for diode, when it is conducted, after the conduction, when it goes to cutoff status, there will be a reverse recovery current from diode. And this is also why we can see in waveform here in the right picture, there is a current peak here. This peak is caused due to this reverse recovery current of diode. At this time moment, we focus on the turn-on process of IGBT test, the electrical and the thermal parameters related to the on process of IGBT, and also we can check the details of reverse recovery process of the corresponding diode. And after time moment T2, we go to T3. The current will rise linearly again, and it is similar compared to the first on status because now the reverse recovery current disappears and we get only this current pass through the load inductance to our bottom IGBT. And after this time duration, we will turn off the bottom IGBT again. Then we will go to the time moment T3. In this turn off process, due to the existence of the stray inductance L delta, a peak voltage will be generated and adding on the DC bus voltage and then applying to the IGBT, which is the waveform we can see in this right picture here, this delta V. We will say the peak voltage here, we named it as Vmax, voltage maximum voltage, which is equal to VDC plus delta V, and the delta V is equal L delta times di divided dt. The voltage is produced due to the stray inductance and the turn off di divided dt. The larger the stray inductance is, the greater the turn off current is. And the higher di divided dt is, the higher the voltage peak is. And then the greater the turn off over voltage risk of the module is. So normally this voltage peak cannot exceed 90% of the threshold of our module voltage level. So it's very important to keep our complete system be operated in a safe operation area. Of course, if you expand the time duration between T0 and T1, which means that we let our current rise continuously in this first on stage, and you turn off the IGBT, you will also see this spike in first on process now because your current is much higher. This is what you can see in the real test. But in this presentation, in this script, we just make everything easier for you to understand. At this T3 moment, we will focus also on the turn-off process of IGBT and test the electrical and thermal parameters related to bottom IGBT at the off moment. The captors above basically cover the relationship between voltage and current and the time for each phase, also including the corresponding waveform. Then a question: how can we guarantee that after passing the single and the double pulse test, the IGBT is still safe when using? Based on our experiences, we would like to recommend the test condition which covers most of the application conditions to converter design. Generally, the DC bus voltage is set at 1.2 times of the off-bus rated voltage. For example, the bus voltage of converter is 500 watt. During the test, the bus voltage will probably go up maximum to 600 watt. And the current flowing through the IGBT is set as twice of the module rated current. If our module is like a 300 ampere module, then the maximum current should be set at 600 ampere. And the entire turn-on time, T1 plus T3, is recommended to be less than 100 microseconds. T2 is the off time, recommended to be greater than 10 microseconds because a larger turn-on delay. When measuring IGBT, the load inductance is generally 10 to 100 microhenry. Our largest current will be dependent on the DC voltage, the on-time T1 plus T3, and the load inductance. So finally, here is a typical double pulse test waveform. The left picture is a complete double pulse waveform, which is the same as our theoretical analysis, and you can see that T1 is much longer than T3 because we cannot let our current in the second on process rise too much. It will damage our module and our system. And we take T2 and T3 moment waveform for detailed analysis. The on and off process are the same as the theoretical analysis, so we can say now our analysis is correct. It is same like the real test. And above is the principle and the significance of the double pulse test. So it's a very general introduction of the DPT. Actually, from this waveform, we can see much more than I described today. But it's very detailed, and you need to do the test by yourselves in your real study and work. If I only tell you what will happen, sometimes it makes no sense. So in next video, we will bring you a transformation from our theory to practice. We will teach you how to build a double pulse test platform and talk about the problems that will be encountered when building and testing. So thank you for your watching. See you in our next video. Thank you. Bye.